Let's continue chapter 4 and talk about commutative, associative, and distributive laws of matrices. So first is the matrix addition. And first let's talk about the commutative law. So it's very easy to understand. It says that matrix A plus matrix B is just the matrix B plus matrix A, right? So the order of them doesn't matter for the addition. So for example, if 1, 2, 3, 4 plus 0, 7, 2, 8, we know that the result should be the addition of the corresponding pairs, right? So this should be for the first element in the first row, first column here, it should be the summation of 1 and 0, right? The corresponding position elements. And for the 9, it should be 2 plus 7, and the 5 should be 3 plus 2, and 12 should be 4 plus 8. All right, so the 1, 9, 5, 12 should be the result of the addition of the corresponding positions in the two matrices. And if we change the order, we can see that if we change to B plus A, so 0, 0, 7 to 8 plus 1, 2, 3, 4, when we calculate the addition, we still take the summation of 0 and 1 and summation of 7 and 2, and we add 2 and 3 and 8 and 4 together. So the results don't change, right? So when we change the position or change the order of A and B, the addition doesn't change. The addition result doesn't change. So that is a commutative law. Second is called associative law. So it just means that A plus B, and the summation of A plus B and then plus C equals to A plus the summation of B plus C. Okay, so for example, we use the vectors as an example. So this is V1, V2, and V3. So if we first calculate the summation of V1 plus V2, so that will be the summation of 1 and 4 as the first element, and the summation of 2 and 5 as the second element. So that's 5 and 7 here. And then we plus V3, and we can get 12 and 15 as a summation of 5 and 7, and a summation of 7 and 8. Right? So that's how we calculate the addition of vectors. And if we calculate V2 plus V3 first, we get the same thing. So V2 plus V3, first we calculate 4 plus 7, right? So that's 11 here. And then 5 plus 8, so that's 13. So 11, 13 is addition of V2 plus V3. And we calculate V1 plus the summation here, and we can get again 12 and 15. So the combination of the matrices when we are doing the addition doesn't matter. So this is called associative law of matrix addition. Yeah, we only talk about addition here in the first part. So for the addition, the orders and the combination, they don't affect the result. For the matrix multiplication, the most important thing that you need to know is that it's not commutative. So what I mean is that the matrix A times matrix B doesn't necessarily equal to matrix B times matrix A. So for example, we have two matrices here, matrix A and matrix B, and both of them are 2 by 2 matrix, 2 by 2 dimension, right? So they are a square matrices. So from the when we talk about the matrix multiplication, we can see that A times B is able to calculate, right? Because the column dimension of A is 2. This is the column dimension of A. And the and the row dimension of B is also 2. So these two numbers are equal to each other. So it's conformable, right? So in this case, we can calculate A times B. And the resulting matrix, matrix C, should also be of dimension 2 by 2. So this 2 come from here, and this 2 come from here, right? So the resulting matrix C should be of dimension of the row dimension of A and the column dimension of B, but the remaining two numbers combining together. So this is a dimension of the multiplication matrix. So this is what we learned before. And so B times A is also conformable. Or we can also calculate B times A because B is 2 by 2, A is 2 by 2. So because the square matrix, so the column dimension of B equals to the row dimension of A, right? Because both the dimension, the row and the column dimension of both B and A are 2. So when we change the order, we can still calculate the multiplication since all of them are 2. So these two numbers are equal, and the resulting matrix, we call that D, should also be 2 by 2 matrix, right? Okay, so we can calculate first A times B. So A times B, as I said, is a 2 by 2 matrix. So we have 4 elements here. The first element, second, third, and fourth, right? So when we are calculating the element at the first row and the first column, we use the first row of the first matrix, right? A is the first matrix, B is the second matrix. So we use the first row of the first matrix times the first column of the second matrix to get the first element here, right? So this is it's actually not the first row times the first column. It's called the inner product. And the way we calculate it is that to multiply the corresponding elements and then add them together, right? So here, this is 1 times 0, the first element here and the first element here, and then plus 2 times 2, the second element in the row here and the second element in the column here. And then this is 4, which is the resulting matrix, which is the first element of the resulting matrix. And again, when we are calculating the element in the first row and the second column, we use the first row of A and the second column of B to calculate. So that's 1 times 1 plus 2 times 3. So this is 7. Right, 6 is 1, and then this is 7. And so for the third and fourth element, we use the same method as we talked about that before. And then find out, okay, A times B is this matrix. But B times A, if we change the order, we can find that using the same method, right? Everything the same. We can find that the matrix is not the same as A times B. So this is a very important property of matrix multiplication, is that the order of the multiplication affects the result. So A times B is not B times A. It's not the same as in the number algebra, right? Because there are two matrices, and it's very complicated to do multiplication using matrices. So if you change the order, you will change the result, right? But there's one exception, is that if A or B is identity matrix, and we haven't talked about that, but we'll talk about that. very soon, right? If A or B is an identity matrix, then A times B equals to B times A, right? Or A is the inverse matrix of B. We'll talk about that later on. Okay, we'll talk about these two concepts later on. Another understanding of why the matrix is not cumulative, the matrix multiplication is not cumulative, is to give you this example. So again, A times B, right? Suppose A is a 2 by 3 matrix and B is a 3 by 2 matrix, right? If I calculate A times B, then the resulting matrix should be 2 by 2 of dimension, right? Because the 2 by 2 comes from the row dimension of A and the column dimension of B. But if we calculate B times A, so B is 3 by 2, A is 2 by 3, and the resulting matrix is 3 by 3 dimension, right? As I said, you can, because the 2 and the 2 are the same, so B and A are conformable. And the resulting matrix, the multiplication, the dimension of D should come from the row dimension of B and the column dimension of A. You combine this number and this number to get a new dimension of the multiplication matrix. Again, this number and this number are the dimension of the new matrix here. So we can see that A times B is a 2 by 2 matrix, but B times A is a 3 by 3 matrix. So clearly C and D are not the same, right? So B times A is not equal to A times B because even the dimensions of the new matrices are different. Here in the example, we use a square matrix. So it doesn't matter, right? Because A times B and B times A, both of them are 2 by 2 matrices. 2 by 2 matrices. But if we use a different dimension of the two matrices, the resulting matrices may not have the same dimension as before, as in this example here. So that's why matrix multiplication is generally not commutative. And then we talk about the associative law of matrix multiplication. So this means that A times B and then times C equals to B times C first and then times A. So A times the product of B times C, right? So first combine A and B or combine B and C. But if you keep the order A, B, C, and this order A, B, C, the general order are the same, then they are the same, right? Anyway, I mean, if A times B times C, so this is called the general order, and you don't change that. So A times B times C equals to A times B first and then times C, or A times B times C, right? We'll first calculate B times C and then times A. But A times B times C is not equal to C times B times A, right? You cannot change the order here, right? It doesn't matter if you calculate A times B or B times C first, but you cannot change the order A, B, C, right? If you change the order, it's not associative law, right? Because the matrix multiplication is not commutative, so you cannot change the order. So if A is a n by n matrix, B is a n by t matrix, and C is a t by s matrix. So the resulting matrix, if we time A and B and C, the resulting matrix D should be of dimension m times n by s, right? Because, so here's m, here's m. If we times A and B, A and B. So A is m by n, B is m by t. So this matrix, A times B, this matrix should be m by t, right? So if we combine A and B, so this should be m by t matrix. And then we calculate this m by t matrix times the matrix C. So the resulting matrix should be m and s, m by s, right? But if we combine B and C first, so B is m by t, and C is t by s. So the resulting matrix should be m by s, right? So if we combine B and C, so this yields a m by s matrix. And then we times A in front of that. So that's m by n times the n by s. So again, the D should be m by s of dimension, right? So whether or not you combine A and B first or B and C first, the resulting matrix should have the same dimension, right? Okay, so this is called associative law. And the third thing is called distributive law. So matrix A times the summation of B and C should equal to A times B first, and then plus A times C. So this is just like the number algebra you learned before. Before. But pay attention that you cannot write this as B times A plus C times A, right? So this is wrong, right? Because as I said, A times B is not the same as B times A in matrix multiplication. So even if you can get rid of these parameters and then say that, okay, A times B plus A times C, but you cannot change the order of A and B or A and C, right? You cannot say something like this because it's not cumulative, right? And B plus C, the summation of B and C and then times A, you can also get rid of the parameters by saying that it's equal to B times A first and then plus C times A, right? But again, this is not equal to AB plus AC, right? Because you cannot change the order of the multiplication itself, but you can get rid of the parameters in this way. Okay, and then next we'll talk about the identity matrices and known matrices. So first is the identity matrices. So IM is called an identity matrix of dimension n by n. So first thing you need to know that identity matrices are square matrix. So IN, identity matrix of dimension n, means the matrix is n by n, a square matrix. And if I said I3, that means that this is an identity matrix of dimension 3. So that means that this should equal to this thing, right? So let me talk about that. In general, the identity matrix of dimension n, or the n by n matrix, should equal to this thing, right? So this matrix means all the diagonal elements are 1, but all the other elements are 0, right? Only the diagonal elements are 1, and all the other are 0. So for example, if this is an identity matrix of dimension 2 or 2 by 2 square matrix, then it should be 1, 0, and 0, 1, right? Only the diagonal here is 1, and all the other part, we only have 4 elements here. So we only have 2 zeros here in the other part, right? So this is called identity matrix. So if this I3, that means that is 1, 1, 1, right? If we write things out, it should be 1, 0, 0, 0, 1, 0, 0, 0, 1, right? It's like this. Only this line, the elements in this line, from the top left to the bottom right, this line are ones, and all the other positions of the elements are 0. And if it's I4, that means that we have this is a 4 by 4 square matrix, right? And only the elements on this line, on this diagonal, is 1, and all the other positions are 0. So this kind of matrices are called identity matrices, right? So identity matrices, the properties of this kind of matrices are like 1, the number 1 in the number algebra. Right, we know that, for example, 1 times 2 equals to 2 times 1 equals to 2, right? So this is what we learned in number algebra. So in matrices, the 1 is like the identity matrices here, right? And the 2 is like other kind of matrices. But the properties of identity matrices are just like the number 1. So let's look at these properties. For any matrix A, the identity matrix times A equals to A times I equals to A itself, right? So any matrices A, if we times the I, no matter in the front or no matter in the, so no matter it's I times A or A times I, right? No matter how you multiply the identity matrix with the matrix A, you can get the matrix A itself in both cases. So just like number 1 times any kind of number, the resulting number is still the number itself. Right. But there's one thing that you need to know, is that this I didn't write out the dimension of the I, right? If I say I2, then it's a dimension of 2 by 2. If it's I5, then it's a dimension of 5 by 5 square matrix. But I didn't write out the I with dimension here. It's because the dimensions may change, right? So for example, if A is a 3 by 4 matrix, if we calculate I times A, right? So A is 3 by 4. If we want to calculate I times A, then we have to find the identity matrix with a dimension of 3 by 3, right? Because the column vector, the column dimension of the first matrix should be equal to the row dimension of the second matrix. And the row dimension of A is 3. So we have to find an identity matrix that is conformable with A. So the only kind of dimension that the identity matrix has is a 3 by 3 matrix, right? Only in this way we can calculate I times A, right? Because the 3 here equals to 3 here, right? If we use a 2 by 2 identity matrix, then we can now calculate this matrix times the matrix A because they're not conformable. Okay, so the resulting matrix should be of dimension, so for example, I'll call this D. So I times A equals to D, and D should be of dimension 3 by 4. Right, we combine this number and this number. So we get the resulting matrix. But if we calculate A times I, so A is 3 by 4. So we want to find out a matrix I so that it's conformable with matrix A. So we know that A becomes the first matrix here, right? Here, A is the second matrix, but in this kind of multiplication, A is the first matrix. So the column dimension of the first matrix should be equal to the row dimension of the second matrix. So that means that we have to find a 4 by 4 matrix to make them conformable. Right, so I has to be 4 by 4. And the resulting matrix, I call this E, should be 3 by 4 of dimension. 3 and 4. So we can see that when we calculate I times A, and A times I, we use different identity matrix. That's because the column vector, the column dimension and row dimension of A are not the same. One is 3 and the other one is 4. So when we are multiplying a matrix, before A or after A, we have to use a different identity matrix. But the results are the same. Right? The results are the same. The matrix D and the matrix E should be the same thing. They should be just the matrix A. Right? Whether or not we use a different identity matrix, it doesn't matter. We just consider the identity matrix as 1, number 1. Right? No matter what kind of identity matrix you use, just consider it to be number 1. And then when we calculate I times A, we can just cancel this I and the resulting matrix should be A. Right? And the matrix E should also be A. So let's see an example here. So here, this is our matrix A. It's a 2 by 3 matrix. And so when we calculate I times A, because A is 2 by 3, so this I has to be a 2 by 2 matrix, right? To make the two numbers the same and is conformable. So I should be a 2 by 2 matrix like this. 1, 0, 0, and 1, right? So let's calculate the multiplication of these two matrices. I'm going to skip how to calculate this because I've talked about how to calculate matrix multiplication before, right? So first, this row and this column, and this is this element here, and the first row, second column here, and the first row, and third column, and then second row, first column is here, second row, second column is here, and the second row, third column is the last one. And then we can find that it's still 1, 2, 3, 4, 5, 6. You can calculate that yourself. And if we calculate A times I, because A is 2 by 3, so I has to be a 3 by 3 square matrix. So the two numbers are the same. And the resulting matrix should also be 2 by 3, right? 2 by 3. So A is 1, 2, 3, 4, 5, 6. So I should be a 3 by 3 matrices.